Okay, good morning to all. So, this is our 37th lecture and final lecture for the course Compressible Flow and Gas Dynamics. So, in today's lecture, we will talk about two important topics. First is conical flow. So, if you remember, we have discussed the two-dimensional flow over a wedge during our earlier discussion, and at that time I told you that in case of conical flow, because there is one more boundary available for expansion of the fluid, so that's why it behaves slightly differently in comparison to that of the two-dimensional wedge flow, and we will take up this in the later lectures. Okay, so that is the first part, and second part is whenever we solve the problems of compressible flow, then we have one very important method which is called as method of characteristics, and it is having huge amount of advantage if you have to find out the numerical solution of compressible flow problems. Okay, so as I told you that when we study the compressible flow, we are able to find out the solution by putting certain set of assumptions, and that also to certain set of problems only. Okay, and under mainly for subsonic and supersonic flow conditions. But when we are having the involvement of transsonic and hypersonic flows, then our physical behavior of the phenomenon or flow becomes very complex and challenging, and under these conditions the assumptions which we have applied to find out the closed form solution of governing equations, these assumptions will not be valid. And second important point is, if these assumptions are not valid, then we have to solve the exact non-linear governing equations which we are having. Okay, so if we have to solve exact non-linear governing equations, then we require the numerical methods. Okay, and implementing numerical methods for full non-linear equations is also challenging. So what we do, we try to take the help of method of characteristics, because it gives us kind of grid kind of characteristic network along which our governing equations becomes the compatibility equations, and these compatibility equations are mostly in the form of ordinary differential equations, so their numerical solution is actually quite easy. And even for the you can so as we see in our computational fluid dynamics course, that we are having different discretization techniques: finite difference, finite volume, and finite element. So the simplest of all these is finite difference method. So the kind of characteristic network we get over here, over that network actually we can easily apply the finite difference method also. Okay, so that is the benefit of this method of characteristics. Obviously we will not be going to see the examples of method of characteristics in details, but a brief idea of method of characteristics or its philosophy I will try to discuss over here. Okay, so let's first talk about the formulation of conical flow. So formulation of conical flow is mainly based on, as I told you in the previous lecture also, it is based on the Taylor-Macol solution. Okay, so whatever the solution was presented by Taylor and Macol, based on that solution actually the formulation of conical flow is actually based. Okay, so what we have over here, if you see this is x, y, z Cartesian coordinate system, and then over this also I have drawn the spherical coordinate system also. So you can see over here, this is direction r, this is angle theta, and this is angle phi. So these are nothing but the spherical coordinate system. So if I have any location, anything at angle r, at angle theta and radius r, then its projection on this plane will give me angle phi. Okay, so this dash, the structure drawn by dashed line over here is nothing but an axis symmetric cone. So you can see in this conical structure what we are having, this is the boundary, and this boundary basically we are revolving along the phi, and what we are getting, we are getting nothing but a complete three-dimensional cone structure. Okay, and in a typical flow situation, what I can take, that v theta is the semi free stream velocity of the v infinity is the free stream velocity of the flow. Okay, so this is how it is approaching the cone. Now typically you can see one thing I have told you in the previous lecture also, that because this is the planar structure and this is rotated 360 degree along the phi direction, so whatever value of the flow field we are getting at a particular location of phi, same will be applicable for the complete thing. Okay, so it means that properties are not varying along the phi direction. So if these are not varying along the phi direction, so typically I can write del by del phi equal to 0. So anything involving del by del phi I can substitute directly to 0, because this is nothing but an axisymmetric situation. Okay, so about this z axis we are having the symmetric flow field. So we can into our mathematical analysis also we can introduce this by writing del by del phi equal to 0. Another important point, if you recall from the previous lecture, I have told you that if this is the vertex, from this vertex I can say that multiple rays are going, and along a particular ray my properties will be constant. Okay, so if I choose a single ray, so along this ray I can say the value of del by del r also will be equal to 0, but this has to be only along a particular ray. So if I move from this ray to this ray, then once again what we will be having, we will be having different values of property. Say here I am having different density rho 1, here density rho 2, here density rho 3, but this rho 1 for the entire ray at any point if I go, that will be rho 1 only. So for a particular ray the variation in radial direction has also diminished. So that is something which we have seen or people have seen from the experimental evidences. Okay, this thing is clear. So mathematically I can introduce these two things. Due to the axisymmetric nature of the flow, del by del phi will be equal to 0, and for a particular this ray I will be having del by del r equal to 0. Now this type of cone can be simply presented something like this. So here you can see this is the cone surface, and this cone surface is making an angle theta c with the direction of the free stream velocity. Okay, and then what I have done, arbitrarily I have chosen any ray over here. Okay, and that ray is say at an angle theta. So for this ray, if I take any point along that ray, then the components of the velocity will be, this is the radial direction. So along this radial direction, component of velocity will be Vr, and this is the theta direction. So along this my component of velocity will be V theta. Is this point clear? Then say this is the shock wave, because what we are trying to do, we are trying to find out the solution for conical flow under supersonic regime. So when we are talking about the supersonic regime, obviously we will be having the presence of a shock wave. Okay, so this is the shock wave which I have considered over here, and this shock wave is making an angle of theta s with the direction of the free stream velocity, and free stream velocity is having magnitude v infinity. So this is my given flow situation over here. Now we know that our continuity equation is nothing but divergence of rho into v vector equal to 0. So this is my continuity equation. Now as my flow situation is nothing but in the spherical coordinate system, so whenever I have to calculate this divergence of rho into v vector, this I have to calculate in the spherical coordinate system. So obviously in spherical coordinate system, del operator will be having different than del by del x and del by del y. So you can see the del operator will be 1 by r square del by del r, 1 by r sin theta del by del theta, 1 by r sin theta into del by del phi. So this will be your operator del operator in spherical coordinate system. So if I write, so it is like 1 by r square into del by del r, and then I have, this will be what? Unit vector in which direction? Will it be I cap, j cap, k cap? I, j, k are coordinates in unit vectors in Cartesian coordinate system. Okay, so here I will be writing I r, then second term with that I will be writing say I theta, third term with that I will be writing I phi. Fine, because now our directions in spherical coordinate systems are r, theta and phi. Clear? So typically if you apply, so I am not writing this del operator in detail, but you can see over here. So this is the del operator which is given over here. And now if you calculate uh, divergence of rho v vector in spherical coordinate system, so you will be getting some equation like this, where del by del r is having dependence on vr, the radial component of the velocity. Del by del theta is having dependence on v theta, which is the v theta and sin theta. So v theta is the component of velocity along theta direction, and this v phi, which is the component of velocity along phi direction. So now in the next step, what is done, basically these derivatives are expanded. Okay, so now this is nothing but the expanded form of the derivatives. Clear? Once we have got the expanded form of the derivatives, then what we can do, we can introduce, because this conical flow is now an axisymmetric flow situation, and this type of axisymmetric flow situation is also referred to as quasi two-dimensional flow. Okay, because when we introduced the axisymmetric assumption, immediately my dependence in phi direction has become zero. Like in case of wedge, what we do, in case of wedge we introduce the planar symmetry condition. We consider that wedge width is actually infinite. So if wedge width is infinite, then at every plane along the width of the wedge, my flow structure will be identical. So considering that, we don't solve the variation of the flow in z direction, because it is not varying. At every plane we are saying that flow is same. So we consider that as a two-dimensional flow situation in Cartesian coordinate system. So similarly, for a conical case, we are having quasi two-dimensional flow or axisymmetric flow situation in nothing but the spherical coordinate system. Okay, so that is the reason that any term involving del by del phi I can equate equal to 0. So this is the term over here. You can see this is the complete term involving del by del phi. So this term I have substituted equal to 0. If I have substituted this term equal to 0 and done some algebraic manipulations, then this will be my continuity equation. Okay, so this is nothing but my continuity equation over here, and once again the terms inside the bracket are also simplified, and finally I am getting this final form as nothing but my continuity equation. Okay, so if at the moment you see this continuity equation, how many variables you are having? One variable over here is rho density, second variable over here is VR, okay, and third variable over here is v theta. So these are the three different variables at the moment we are having, and so these are the dependent variables. And what are the independent variables over here? So independent variable, if you see over here, the complete independent variable is only now theta. All these parameters are actually depending upon theta only, because where we are having variation of del by del r, that also considering a rho I can equate it equal to 0. Okay, if I say that this continuity equation is applicable only along a single ray, okay, in that case what I can do, I can even equate del by del r also equal to 0, and finally I will be getting this as the final form of continuity equation. And in this continuity equation I have three variables, rho, vr, v theta, and these all are depending upon a single variable theta. So situation is very clear. It means in a conical flow I can say that if this is the shock wave and this is the cone, then what will be happening, if this is my one ray, this is another ray, this is third ray, so solution, this equation has to solve for each ray. So we have to march solution in theta direction, because along the ray solution is constant. So if I know the solution at for any single ray, then I can, that will be applicable for the complete ray, then I can march that to the next ray. Then once it is known at this point, then I can march to the next ray. So like that we can actually solve. So for first at the boundary, as a boundary condition or initial formulation, we should know the solution, then we can actually march it along different theta directions. But over here you can see that we are having three variables which we have to determine, and we have one equation. So it means it is not feasible at the moment. So what we have to do, we have to get more equations, and also till now we have only seen the continuity equation. Okay. Now let's come to the second situation. So second point is, in case of conical flow, always my this shock wave will be nothing but a straight line. It will not be curved if it is attached to the surface. So if wave this shock wave is a straight line, it means strength of the wave is not changing. So strength of wave at each and every location is same. So if strength of wave at each and every location is same, what is the meaning of this? The meaning of this, whatever fluid is coming from this side, whenever it will be reaching behind the shock wave, rise in its entropy will be same everywhere. Okay, what will be the change in its entropy? That will be same everywhere. If you do here, if you do here, or here. So any streamline, whether if you take just at this end or at this end, behind the shock wave, entropy of that particular flow field will be everywhere the same. If entropy of the flow field is same, it means gradient of entropy is equal to 0 for this situation. This point is clear. Another important point we have is, this is nothing but an adiabatic situation. We are not doing any heat transfer over here. So if this is an adiabatic situation, then we know from energy equation that at these two regions, one is region over here, another region over here, in these two regions, total enthalpy remains constant for adiabatic flow situation, because total enthalpy changes only when either we are adding energy or removing energy. If energy is converting from one form to another form within the flow field, then in that case total value of that enthalpy will always remain the constant. Okay, so unless or until we are not doing any work or heat interaction over here, so our for adiabatic flow situation total enthalpy will be 0. So that way gradient of H naught will also be equal to 0. So now if these two terms are equal to 0, from Crocos theorem, we know that flow will be irrotational. Okay, that is something which we know from the Crocos theorem. So Crocos theorem is combination of the momentum and energy equation, and that tells us that if we don't have gradient of entropy and gradient of total enthalpy, in that case our flow will be purely irrotational. Okay, so that is the reason for this conical flow, what I can do, I can apply this condition, that curl of velocity vector will be equal to 0. Okay, so now these are the unit vectors ER, RE theta and R sin theta E phi. So these are the unit vectors in R theta and phi direction, and these are say our one by this gradient operator, and these are the velocity values. So this 1 by r square sin theta is common in throughout. So by solving this curl, this is the detailed equation I am getting. Okay, now in this equation what I have to do, I have to introduce the two conditions. What are the two conditions? Del y del phi equal to 0 and del y del r equal to 0. You introduce these two conditions. If you do so, finally you will be getting out of this equation that v theta is equal to del vr by del theta. Okay, so the condition of irrotationality is giving me that v theta is equal to del vr by del theta over here. Okay, now what I can do, I can so I have got only two equations at the moment, but I have three variables. Okay, so let's once again go to find out the third equation. So we know that dp is equal to minus rho v into dv, and v square for this conical flow situation will be vr square plus v theta square. Okay, so now if I do this substitution, then dp will be equal to minus rho, and in place of v I can put velocities in the form of vr square and v theta square. So this way, this is equation 1. Then another equation I can introduce for the isentropic flow, that dp by d rho at constant entropy has to be equal to a square. Now if I substitute the value, then d rho will be becoming dp by a square. Now to calculate d rho, what I will do, I will substitute back pressure over there, okay, from this equation number 1, and finally I will get d rho by rho equal to minus 1 by a square vr dvr plus v theta into dv theta. Is this one clear? This equation, you know, na, this is nothing but our momentum equation only, okay, when we have deduced it for the irrotational flow. So this is nothing but our Euler's equation only. Okay, we also know that h naught will be constant and h naught will be h plus v square by 2. Now let's consider that, okay, so this is my third equation. First let's talk about this one only. So this is my third equation. So now I have got three equations, so I can solve this solution. Okay, now what we will do, we will try to further simplify this set of equations. So in order to do so, we will take some reference velocity. Okay, so how we will take reference velocity? For that we will take the help of this energy equation. So we know that h naught is equal to constant, which is h plus v square by 2, and this I can write equal to Vmax square by 2, considering that if I convert all the enthalpy of the flow into velocity, then what will be happening? I will be having the maximum enthalpy, maximum velocity. Okay, so if you are having, say, flow with some enthalpy and some velocity, now you are allowing it to expand such that its complete enthalpy becomes equal to 0. Okay, so all the enthalpy what flow is having, that is going to convert in velocity. Okay, so ultimately whatever the velocity we will be getting, that is the maximum velocity what we can achieve from a given flow situation. Is this point clear? So if you convert, h naught is total enthalpy, so if you convert your all enthalpy into flow, then after that there will be no potential for further expansion and then achieving the more velocity. So then this h plus v square by 2, considering h naught equal to constant, gives us nothing but Vmax square by 2. So now we have done this many times. For a calorically perfect gas, this can be represented as a square by gamma minus 1 plus v square by 2 equal to Vmax square by 2. So from here you can calculate the value of a square as gamma minus 1 by 2 into Vmax minus v square. Vmax square minus v square, you can write v as nothing but vr square and v theta square. And then in your dp by rho, this a square term you can replace with this. So this is the a square, and this a square now I will substitute in my dp by rho. So if you do, then dp by rho will become, sorry, this d rho by rho will become something like this. Now what I have done, I have basically divided this equation by d theta and then done some algebraic manipulations in order to find out the value of d rho by d theta. Okay, so this is my value of d rho by d theta, and if you go back to continuity equation, this is your continuity equation. In your continuity equation also you are having one d rho by d theta. So what I can do, I can substitute back this d rho by d theta. Here also I have written the continuity equation, so I can substitute back this d rho by d theta here. So if I substitute back, then my continuity equation takes this particular form. Okay, so this is nothing but my continuity equation after I have substituted d rho by d theta. Is this point clear? And if you further expand this, then you will be getting your continuity equation something like this. So the equation which we have got over here, this continuity equation is something which is called as Taylor-Macol equation. This is nothing but the Taylor-Macol equation. Is this one clear? So now we have three equations. One is this continuity equation, the Taylor-Macol equation. Second, we have V theta equal to dVr by d theta. So if I do dV theta by d theta, then what it will become? D square Vr by d theta square. So I have just taken d by d theta of this. Now in the Taylor-Macol equation also I am having one term dV theta by d theta. So this I will replace with this. So if I do so, then I will get this equation. What is the beauty of this equation? The beauty of this equation is that now this complete equation is showing variation of a single parameter Vr as function of theta. Is this one clear? The benefit of this equation is from this term the dependence of all other parameters we have completely eliminated and written in the form of a single variable Vr. Okay, so that way now Vr is a sole function of f of theta, so it means I can independently solve this equation to find out the value of Vr. Is this one clear? So now for a given value of theta, I can independently solve this equation to calculate the value of Vr. Okay, so another important form of this equation which is of interest for many times in non-dimensional analysis. So what we can do, we can write non-dimensional velocities v dash as v by v max. So similarly, if I have to write vr dash, that I will be writing vr as vr by v max, and if I have to write v theta dash, that will be v theta by v max. So I have non-dimensionalized the velocities. Okay, so if I try to write down this equation in non-dimensional form, then v everywhere I have to replace with v dash into v max. So here v I have to replace with v dash into v max. So if I do so, I get this equation which is nothing but the non-dimensional form of our continuity equation or non-dimensional form of Taylor-Macol formulation for conical flow. Okay, so now another important thing is this v by v max v dash ultimately can be represented in terms of Mach number, so that if from the solution of this equation I am having value of Vr dash known, then I can calculate the corresponding local Mach number. Okay, so for doing that, what we do, we write this energy equation, this we have already written, and then what I do, I divide this equation throughout by v square. So if I divide by v square, it will be becoming a by v square, this v will cancel out, v max by v square, and ultimately this becomes 1 by Mach number square and v max by v. So v max by v is nothing but 1 by v dash. So from here I can solve for v dash, and then this tells us that if I know the value of v dash, okay, what is v dash? Square root of vr dash square plus v theta dash square. Okay, non-dimensional total velocity. So if I know the total non-dimensional total velocity at any location, then I can calculate the corresponding value of the local Mach number. Okay, or if I know local Mach number, I can relate it to v dash. This is the important relation. Why? Because this particular equation will give us only the solution of Vr dash, only the solution of Vr dash. Then using this equation, I can calculate V theta dash. Once Vr dash and V theta dash are known, then I can calculate V dash. Okay. But if I have to calculate all other properties such as density, pressure, temperature, enthalpy, etc., then what I have to do? Because for calculating density, pressure, temperature, etc., we must know the Mach number. These are always dependent upon Mach number, as we have seen in the earlier formulations. Okay, so once we have calculated velocity, then from that velocity we should first get the value of local Mach number. Once local Mach number will be known to us, then by using the earlier relations, which gives the relationship between Mach number and the properties, using these relations actually we can calculate all other properties. Is this point clear? What is the need for obtaining or writing this particular equation? So that is the need actually. Okay, so now it is important to know that this equation is still having so many terms, though it has become ordinary differential equation, because our sole dependence is on a single parameter theta. So that's why wherever we were having in the initial formulation del by del theta, that I can replace with d by d theta. Okay, though it is an ordinary differential equation, but still it is having non-linear terms. Okay, so due to this non-linearity, I cannot find out its closed form or analytical solution. So if we have to solve this equation, we have to go for the numerical procedure. Okay, and the numerical procedure which is employed, that is actually inverse approach. What is inverse approach? Let me explain. So what we will be considering, we will be starting with the point that let us assume I have a shock wave at angle theta s. So what I have done, I have assumed that I have a shock wave at an angle theta s, and that is experiencing a free stream Mach number of m infinity. Okay, so important point is, first step is this. I have assumed that I have a shock wave, and this shock wave is actually experiencing this m infinity as the Mach number, free stream Mach number. Okay, now what will be happening? This is the direction of free stream velocity, and this is downstream. On the downstream of this, flow will bend. So say this is my new direction and new velocity v dash. Okay, and in reference to the free stream, let's consider that flow has deflected through angle delta. Okay, now the streamline is passing through shock wave at this point. Is this one clear? Through this point, obviously I will be having some ray also in the radial direction. So if this v dash is the velocity, the component of this velocity are vr dash and v theta dash. Okay, so first thing what we have assumed, that we are having a shock wave and it is at an angle theta s, then m infinity is my free stream Mach number which it is experiencing. Now important point is, this shock wave is nothing but, typically this problem over here, this streamline is nothing but becoming like a simple case of oblique shock wave. You have an oblique shock wave at an angle theta s, where a flow streamline is coming and then it is actually bending. Okay, so what is this? Earlier, if you recall, we have done the two-dimensional wedge flow. So from two-dimensional wedge flow solution, I can find out the value of m2. Is this one clear? This I can find out from oblique shock wave relations. Okay, is this one clear? Oblique shock wave relations are nothing but algebraic equations. Let me once again remind you back to the theta beta m diagram. So basically I am talking about that thing, theta beta m diagram. So you are having the value of beta known. Beta we have replaced with theta s, and m is our m infinity. Okay, so if I know the value of beta, means if I know the value of theta s and if I know the value of m infinity, then I can calculate the value of theta from theta beta m diagram. What was theta? Theta was the deflection of streamline on the downstream of the shock wave from free stream direction. Over here theta is something different. Over here theta we have assumed the direction. So this deflection theta, the commensurate parameter for theta in this present formulation is delta. Is this point clear? So now I can say that using the oblique relations I can calculate value of m2 and delta. Is this point clear? If m2 and delta are known, then in the previous slide only I have a relation in between m and v dash. I have relation between m and v dash. So if m2 is known, from m2 I can, using the relation from previous slide, I can calculate value of v2 dash. Is this point clear? Once v2 dash is known, delta is also known, then what I can do? I can calculate the values of vr dash and v theta dash. This will come from the geometry only. So this will come only from the geometry. So it means just by applying just by assuming the shock wave angle theta s, okay, I have got the values for this just on the downstream of this shock wave. Now what I have to do, if I know the values at this ray, I have to transform these values to next ray. Okay, where is your next ray? Next ray is, say, what I have done, I have divided this whole angular domain in the form of number of rays, and all these rays are separated by an angle of delta theta. Okay, so now for first ray I know the solution, I know the value of Vr dash, so I have to calculate value of Vr dash for the next ray. What I will be doing for that? I will be solving this equation. Sorry, this is Vr dash equation, yeah. Say equation number A. So I will be numerically solving equation number A. This is an ordinary differential equation. For solving this equation, I can apply actually our RK method. Okay. For solving non-linear ordinary differential equation using the numerical procedure, I can apply over here Angekutta method. Okay. So using that method, I can solve it. So I will be using this numerical method to calculate the value of Vr dash at next ray. Okay, at next ray. And then after this, once Vr dash is known at the next ray, then using relation, one more relation we are having, V theta equal to dVr by d theta. So then using the relation, this relation I can calculate value of V theta dash. So now Vr dash and V theta dash are known at this ray. Then what I have to do? I have to further transform. Now I know the values at this point. Then once again numerically I have to solve and march solution to next ray. This way I will keep on continuing till my V theta is becoming 0. Once my V theta becomes 0, the meaning is that I have achieved the solid boundary. Is this point clear? This is important to know. Okay. So once my V theta is 0, what is theta direction? This direction. If in this direction there is no velocity, the meaning is boundary is impermeable. That will be only the case if I have a solid object over there. Okay, so when my v theta dash is becoming 0, it means I have reached the surface of the cone, and that will give me the value of theta c. That is the reason we call this approach as inverse approach. So typically what we have theta c known, but value of theta s is not known to us. Okay, but what we are doing, because that way finding solution is challenging, because at this boundary we don't know all the parameters. I don't know the value of pressure, temperature, density, all the parameters are not known at this boundary. I don't know the value of radial velocity at this boundary. Okay, but contrary, if you go to this, assume a shock wave first, then by using the oblique shock relations, okay, what we have studied earlier, I can find out the values at this boundary. Once I have calculated values at this boundary, then I can march my solution until my v theta dash is becoming 0. That is the reflection of a solid boundary, and corresponding to that, whatever theta we are having, that is nothing but our. But one important point is, so say this procedure you have to do in an iterative fashion, because one time if you do, you may get some cone angle which is not matching to your physical situation. Okay, then you have to try some other value of theta s and then march once again the solution. Fine. So that is the reason, by using this inverse approach, in some of the literature already, for different values of theta s, what will be the corresponding theta c values, these are already tabulated. Okay, so this is a tabulated procedure for given values of theta s and m infinity. For different values of theta s and m infinity, already the different values of theta c are actually tabulated in literature. So you need not to follow the complete procedure, you can just refer to that table, and from there you can find out what will be your cone angle, or for your cone angle what will be the value of theta s. Okay, and now what is the meaning of d theta? So the d theta meaning is that first our solution will be known at theta s, then next I will be calculating solution at theta s plus delta theta, then theta s plus 2 delta theta. This way I will keep on continuing till my theta s plus say n delta theta is becoming equal to theta c. And this will be how we will come to know. This we will come to know once my v theta dash has become equal to 0. Point is clear? So that is the reason this is called as inverse approach. Okay. Any question till this point? Okay, so now you can see the way we were having theta beta m diagram, in a similar fashion I can have theta c cone angle, theta s shock wave angle, and m diagram. So you can see this is the m infinity, this is theta s, and this is theta c represented over here. Along this direction I am having variation of theta c, here I have theta. One important point here, I have not shown this or the text from where I have taken this curve, they have not shown the other part of the curve. So other part of the curve is something like this. So that portion actually they have not shown. So this curve is identical to theta beta m diagram. So for a given cone angle and any known value of m infinity, I have two solutions for shock wave. One is this value of theta s and another is this value of theta s. So this is nothing but higher value of theta s is strong shock solution and lower value of theta is weak shock solution. We can make analogy from our earlier two-dimensional flow. Okay, so this is strong, this is weak, and mostly we will be experiencing the weak shock solution. Okay, and then the way earlier, if you recall, in case of a two-dimensional wedge, if wedge angle is greater than certain value, then our shock wave was becoming detached. Same is the case over here. So you can see for a given value of m infinity, I am having some critical value of Mach number up to which this theta s m diagram is actually given. It means up to only this angle my Taylor-Macol formulation will be applicable. Above this Taylor-Macol formulation will not be applicable. So this is represented over here. When theta cone angle is less than theta c max for a given Mach number, then shock wave will be attached. Once theta c is greater than theta c max, then my shock wave will be detached, even for the conical flow also. Is this point clear? Then important point, so this is the beta and theta s diagram. So basically theta s is shock wave angle and beta is shock wave angle for a wedge, and this is shock wave angle for a cone. So if we try to see in this important diagram, this is the variation for a wedge and this is the variation for a cone. So typically you can say that and this diagram is drawn for Mach number of m infinity equal to 2. So the meaning is, for a given Mach number, value of theta max is actually higher for conical flow in comparison to a wedge flow. And reason is quite obvious, because in case of wedge flow, flow is restricted along the complete plane. So it is having only this top portion for its expansion. Whereas in case of conical flow, flow can expand in this direction as well as along the circumferential direction. Okay, so it is having more area for expansion of the flow. So that is why actually theta c max will be higher. Okay. Then one important point, which is very important, and it is having very much clear distinction for many of the for almost all of the features what we have studied. So here you can see this is your m infinity greater than 1. In case of flow over a cone, majority of the times you will be finding that even if the flow in between the shock wave and cone surface is actually fully supersonic. Okay. However, for certain cases, you can even find that just near the surface of the cone, our local Mach number is less than 1, and near the shock wave our Mach number is greater than 1. Okay. So it means here flow is supersonic, here flow is subsonic. So in between supersonic and subsonic, we must have a ray across which actually we will be having Mach number equal to 1. So that we call as nothing but a sonic line. Okay. So important point is that here what is happening? Transition from supersonic Mach number to subsonic Mach number is taking place, and in this transition we are not having any presence of shock wave over here. So conical flow is a special case where we can experience that transition from supersonic to subsonic flow is occurring without the presence of a shock wave. Okay, so this is one interesting feature of this conical flow. Point, once again let me emphasize, though in majority of the cases you will not find this situation, in majority of the cases you will find this complete entire region is supersonic only. Okay, but in case the flow you are getting subsonic region also, then supersonic to subsonic transition you will be experiencing without the presence of a shock wave. Okay, point is clear? Now let's quickly talk about the method of characteristics. So method of characteristics we will try to see over here for the two-dimensional irrotational flow only. So if you see, for two-dimensional irrotational flow, we have derived velocity potential equation, which was 1 minus phi x square by a square into phi xx, 1 minus phi y square by a square into phi yy minus 2 phi x phi y by a square into phi xy equal to 0. So that particular equation I have written in the form of u and v, where u is x component of velocity equal to del phi by del x or phi x, and v is del phi by del y equal to phi y. Point is clear? So this is nothing but my non-linear velocity potential equation, but I have presented it in the form of velocities. Okay. Now from this equation, if I have to calculate the value of del u by del x, then del u by del x will be, what I have done, I have kept del u by del x on one side and everything on the other side. Okay, so now if I know the value of del v by del y and del u by del y, then I can calculate del u by del x easily. Okay, so what I have done in xy plane, I have considered a line. Say along this line I have different points ij, I comma j minus 1, I comma j plus 1, and this is point ij. Similarly, in next direction I can have point I plus 1 comma j. Okay, so if I have to calculate velocity at point u I plus 1 comma j, then using Taylor series, what I can say? I can say that u at ij plus del u by del x at ij into del x plus higher order terms. If I neglect higher order terms, then I am not concerned about that. Okay, so it means that if I know the value of velocity at point ij, and if I have to calculate velocity at next point I plus 1j, then I must know the value of del u by del x at point ij. Okay, so that del u by del x at ij I have tried to write from nothing but from this non-linear velocity potential equation. Okay, now let's consider that this is a particular line. I am calling it as characteristic line, and along this line, say this all the values of u and v are actually known to us. Okay, so if these values are known to us, then in the y direction I can calculate del u by del y and del v by del y. Okay, so from here I can calculate the value of del u by del x. But one interesting point is that I can have a situation when del u by del x can become indeterminate. Okay, it can become indeterminate if my u is equal to a at point ij. Is this one clear? If u is a, then it will be 0. 1 by 0 will be infinite. Okay, so value of del u by del x will become indeterminate, either discontinuous or indeterminate. So we have one important definition, a line along which the value of gradient either become indeterminate or become discontinuous. That particular line is called as nothing but a characteristic line. So point is important. Here I am having constant property variations, continuous. Okay, so all the values of u, v are continuous in this physical domain, but still in this physical domain I can get some point where my del u by del x will either become indeterminate or will become discontinuous. So that particular line I will be calling as nothing but a characteristic line. Okay, and now this characteristic line is having some analogy with the Mach line also. Okay, so that is something which we have done earlier also. If you recall the case lecture of our shock tube, in case of shock tube, while we have studied the analysis of expansion waves, then we have made this analogy. So you can see over here, this is the typical representation of a shock tube, and in this shock tube, say this is the point where diaphragm was there. So from this point a series of expansion waves are propagating towards the left direction. This is the leading expansion wave and this is the trailing expansion wave. Okay, and say this expansion wave is having velocity a4 because in region 4 my local flow velocity was 0, and here in for all the other expansion waves my velocity will be u minus a, and these are all nothing but the left running shock waves. So if you see on xt plane I can represent these like this. So this is my head shock wave and head expansion wave, and this is my tail expansion wave. So for head expansion wave I have the slope as nothing but equal to a4, and here for all other I will be having the slope as u minus a. Is this one clear? And for tail it will be u3 minus A3. Okay, so one important aspect you can see over here, the mass motion velocity induced by which is induced by the uh, uh, motion of shock wave to fluid, that is given by 2 by gamma plus 1 into A4 plus x by t. Okay, now let's fix a value of t. Say I consider at t equal to t1. At t equal to t1, if I see the variation of velocity along this region, that will be nothing but linear. So you can see this is my region 4 where velocity was 0. Then this is the tail point at time t equal to t1. Point T is my nothing but the tail point, and after this point also my velocity was constant u3 in the region 3. So in this region, here del u by del x is 0, and region 4 also del u by del x is 0. But in between this spectrum from point B to point C, I am having nothing but linear variation of the velocity. So in this linear variation of the velocity, del u by del x will be constant. Okay, so point B and point E are nothing but the points where I am having discontinuity in the values of del u by del x. Is this one clear? So del u by del x on the left side is 0 and right side is some constant value. So it means left hand limit is not equal to right hand limit at point B and C. So it means I have discontinuity in del u by del x. So my point B and C will be nothing but the characteristic points, and corresponding to these points, whatever directions I am having, these will be my characteristic directions. Okay, and all these expansion waves are nothing but the, what are these expansion waves? Weak waves, weak Mach waves. So angle of these expansion waves will be nothing but equal to mu, because these are weak Mach waves. Okay, so that is the reason a characteristic direction is having analogy with our weak Mach waves also. So over here also what I can do, if you see, if I consider that my this angle is mu, then if I try to calculate sine of mu, then sine of mu will comes out to be u by v. What is sine of mu over here? Say this is my base, so this will be perpendicular, that is nothing but u and by v. And for a case when my del u by del x is indeterminate, u is equal to a. So this is becoming equal to a by v, which is 1 by Mach number. So it means this particular characteristic direction I can represent as nothing but a Mach wave. Okay, so this is the analogy in between Mach waves. So all the Mach waves in our flow situation represents nothing but the characteristic directions. Is this one clear? Okay, so typically let's see, this is my equation, non-linear velocity potential equation, and if I consider that my phi x is function of x and y, and similarly phi y is also a function of x and y, then what I can do, I can write d phi x like this and d phi y like this. Okay, now what I have done, I have clubbed all these three equations. So this is first equation, then second equation in the short form, and third equation in the short form. Okay, so if I have to calculate say value of phi xy, then I can apply Cramer's rule over here, and from this Cramer's rule I will be getting this as, I am not going into details of Cramer rule, already you people know. So you can calculate phi xy from these three set of equations using the Cramer rule, and you can get this as numerator and this as the denominator. Okay, so one important point is, for characteristic direction, del u by del x has to be in determinant. Okay, so if you make your d equal to 0, denominator equal to 0, then your phi xy will become infinity, not indeterminate, then this derivative will become nothing but infinity. Okay, but if you see from this formulation, it is very clear that del u by del x is changing from 0 to a constant value, and here a constant value to a 0. So it means derivative of the parameter, any field parameter in a continuous flow field cannot be infinite. Okay, it will be always having a finite value. If it has to be a finite value, so for any flow situation, if d is becoming 0, that is trying to make it infinite. But from the physical nature of the flow, it cannot be infinite. It has to always be a finite value. So as it has to be a finite value, the numerator has also to become 0 so that it can become indeterminate, not infinite. Is this point clear? What I am trying to say that if you have a flow field where you are having continuous variation of the properties, in that flow field, gradient of any flow parameter cannot be infinite, because your assumption is that you are having variation of properties is continuous. Here also you can see that del u by del x is changing from 0 to a constant value. It is not going to infinity. Okay, so it means that, but the situation is, for characteristic direction, d has to become 0. So if d is becoming 0, flow field is becoming infinite. So as it cannot be infinite for a continuous flow field variation, so n has to be equated to 0. Then only n by d will become indeterminate, and if you apply then further for mathematical formulation, that will give you a finite formulation. Okay, so that is the reason what we have to do. We have to do this d equal to 0 to find out the characteristic direction. But if we are doing d equal to 0, n has also to be equal to 0. So d equal to 0 gives us characteristic direction, n equal to 0 gives us nothing but the governing equations which are applicable along characteristic directions, and these are called as the compatibility equations. Point is clear? We are not going to very much details. I am just giving you the brief philosophy of the method of characteristics. So now what we have done, first to find out the characteristic direction, we have done d equal to 0. So this determinant, if I equate to 0, from here I can calculate dy by dx, and obviously because d I am making equal to 0, so this dy by dx has to be applicable along a characteristic direction. Okay, so the solution of this is this particular value. So this is nothing but, what is this? This is nothing but the slope of the line. So if I have a point A and say through this point some streamline is passing and giving us velocity vector v with angle theta from the direction of the from x-axis, then these u and v will be my components of the velocity. Now at this point A I can have multiple directions dx and dy which can satisfy this equation, but I will be only having a unique direction of dx and dy which will be giving me this particular slope and make this denominator d equal to 0. So that particular direction will be nothing but my characteristic direction. So that is something which I have done over here. Okay, so before that let's also try to see. So what I have done now, one important point is, one important point is, inside this square root I have u square plus v square by a square minus 1. U square plus v square by a square minus 1. What is u square plus v square? That is nothing but total velocity v square by a square minus 1, and it is m square minus 1. So square root of m square minus 1 is coming. So it means that if m square minus 1 is greater than 0, then this value will be positive, and I will be having plus minus sign over here. So plus minus sign will give me two values of dy by dx. So two values of dy by dx means I will be having two real directions. Once I have two real directions, then my equation becomes hyperbolic. You can connect back to CFD. Okay. So if my m square minus 1 is greater than 0, then I will be having two real characteristics, and solution and nature of equation will be hyperbolic. If m square minus 1 is equal to 0, then I will be having a single characteristic direction, and this will be nothing but a parabolic equation. And when I am having this less than 1, then I will be having complex roots, and my nature of equation will be elliptic. Okay, so you can see this formulation cannot be applied for elliptic equation, because in real physical space I cannot draw the characteristic directions. So that is the reason for subsonic flow we don't consider method of characteristics, and whenever we talk about the application of method of characteristics, we mainly refer it for the compressible flow situation, that too in the supersonic regime. Okay, and in the transonic regime, what will be happening? I will be having transition from subsonic to supersonic flow. So I will be having transition of equations from elliptic nature to hyperbolic nature. So combination of elliptic and hyperbolic nature we will be. Okay, is this point clear? So all this mathematics you can relate to basic physical situations, and all the things like you are doing in CFD, compressible flow, fluid mechanics, all things are nothing but interconnected to each other. So you should be able to make this analogy actually. Okay, so now another important point is, in this characteristic direction I am having this u and v as the velocities components in x and y direction. So u I can write v cos theta, and v I can write v sin theta. If I do these substitutions in this equation, ultimately I will be getting dy by dx after doing trigonometric uh, manipulations, tan theta plus minus mu. So it means characteristic direction is once again becoming theta plus mu and theta. What is mu? Mu is once again the direction of the Mach wave. Okay, so here you can see this is the xy plane. If I am at point A, this is my streamline. This streamline is making an angle theta with x direction. Then I can say that the slope of my one characteristic direction will be at an angle of theta plus mu. So this is the slope of one characteristic direction, and another I will be having at an angle of theta minus mu. So this is the slope of another characteristic direction. Point is clear? Now, because if I move from one point to another point in the flow field, then corresponding value of theta and mu will be changing. So that's why slope of this point at other points in the flow field will not be same. Slope of point at different points in the flow field will be different. So that is the reason that if I have to draw the characteristic lines, these will be nothing but in the form of curve. Because this is the slope at this point, then I can go to some next point. Here I can find out slope, here I can find out slope. So every point slope will be different, because at every point value of theta and mu will be different. Mu is governed by local Mach number, and theta is governed by local direction of the streamline. So as theta and mu are localized within a flow field, so slope will be different. So that is why our characteristic lines will be nothing but in the form of curve. So the line having positive slope is called as C positive characteristic line, and this is called as C negative characteristic line. And mainly C positive characteristic line is for left running waves, and this is for right running waves. Okay. Now compatibility equation. So what I told you, for compatibility equation, because in order to get the indeterminate value, ultimately numerator has also to be equal to 0. So if I equate numerator equal to 0, then I will be getting this formulation. From here dv by du I can calculate, and dv by du finally will become d theta equal to plus minus m square minus 1 into dv by v. Now this dv by v, if you see, are you able to relate this equation? If you go to Prandtl-Meyer expansion theory, in Prandtl-Meyer expansion theory, our equation was d theta equal to plus minus m square minus 1 into dv by dv, and when we relate dv by dv in terms of Mach number, then I can say that I can write my solution as theta plus some function of m equal to constant and theta minus some function of m equal to constant if my function of m is equal to this. Why I am writing this solution? Because this solution is coming from my parental expansion theory. Okay, and what is coming from parental expansion theory? Same thing can be validated from our previous discussion on sock tube. In case of sock tube, we said that a parameter which remains constant along a characteristic direction, that is called as nothing but a Riemann invariant. So this k minus is analogous to j minus and k plus is analogous to j plus, which are nothing but Riemann invariants in C minus and C positive characteristic directions. So this is some analogy, some initial philosophy of the method of characteristics. Now this can be applied for many problems of supersonic flow into our compressible flow analysis, and this can even be applied for hypersonic flows. Okay, because we are initially considering nothing but the non-linear form of the equation. So if we are considering non-linear form of the equation, then all the non-linearities in our physical domain are actually accounted for. Okay, the only benefit of this method is that if you see your governing equations in actual nature, their actual nature is actually non-linear partial differential equations. But if you solve these governing equations along the characteristic direction, then this becomes ordinary differential equations. As it becomes the ordinary differential equation, their solution is actually quite easy. And what you can do, if you just consider a flow field, at each and every point you will be getting number of characteristic directions. So all these characteristic directions will form a characteristic network, and this network is nothing but what are all these points? All these points can be your node points in numerical framework. All these points can be node points in numerical framework, and along these directions you can apply individual equations which are applicable. These are ordinary differential equations, and you can solve, and you will be able to know the flow field at all these node points. If you know the flow field, then you can easily determine. So benefit is that if you choose these special directions, you are getting your node points in the flow field, and along these special directions you have to only solve the ordinary differential equations, whose solution is quite easy in comparison to the solution of partial differential equations. That is the benefit. Okay, that is the reason majority of the compressible flow, majority of the numerical solution, unless or until people are not going for full scale simulations using finite volume method or other methods, finite element methods, etc. Majority of our compressible flow equations, non-linear compressible flow equations, can be analyzed very easily using finite difference method, because ordinary differential equations will be coming and FDM can be easily applied, and formulations of FDM are quite easy in comparison to other methods. Okay, so let's conclude this lecture, and also with this we are concluding our course as well. The only thing is we have not covered the transsonic and the hypersonic flows, because if we have to go into the details of solution of these two situations, then we have to go into details about the numerical modeling of the compressible flow. So if you people are interested, then you can refer to your textbook from chapter number 11 onwards. So here we have covered chapter up to chapter 10 fully, and then some aspects of chapter 11 also I have discussed. Okay, so for more details on transsonic and hypersonic flows, you can read your book from the chapter 11 onwards. Okay.